Hi, my name is Andrea LeGrand, and welcome to the final video for this class, Material and Energy Balance. And so today we're going to be talking about adiabatic flame temperature. And bear with me, my handwriting might be a little bit off. I did get my booster shot in my right arm because I didn't think about the fact that I had to write on a whiteboard. So my arm hurts a little bit, and so my handwriting might be questionable. But we'll get through this, okay? And so we're going to start with our system. And so our system is a furnace. So let me just write furnace. And so we have going in, we have air, and we have fuel. Okay? And so what we want to do with this system is determine the highest temperature that the, you got a glimpse of my room. It's on a swivel chair, so that's my bad. I don't have any other chair I can set my laptop on. Okay, so we have our air and our fuel, and so we are trying to determine the highest temperature of our products coming out, which is going to be a flame and some hot gas. All right, so with this system, we are going to talk about how this is adiabatic, which we talked about before in adiabatic reversible expansion, where the enthalpy is consistent. So there's no heat lost in this system. And so what that means is that our enthalpy going in is going to be equal to our enthalpy coming out. All right? And so with this, we are going to create some chemical equations to balance out, and we are also going to talk about, well, we're going to code it in Python in a little bit. Bear with me, my brain is scattered. Okay, so our fuel is a mixture, okay? Fuel mixture. And so let's say, for this specific system, we are going to say our mixture is methane, ethane, and propane. All right. And so later on, whenever we code, I will talk about the actual mole concentration of those within the mixture, but that's not really important right now. So what we're going to do now is for each of those sections of the mixture, we are going to put in a chemical equation. So our air isn't pure oxygen. Okay, so in this system, our air is some nitrogen gas and oxygen gas. And so we are given specifically that our ratio of oxygen to nitrogen is 79 to 21. And so what that's going to mean is that we're going to stick a 79 and 21 across every single nitrogen. Okay. And so we have that. We are going to add our first one, which is methane, which is CH4, and then plus oxygen gas, and that is going to give us CO2 plus H2O and that nitrogen gas. And so you might be thinking, well, nitrogen gas, oh, that can cancel out because it's not being used in any other location. Technically, yes, but for our specific system, we don't want to do that because that would be calculating for if the air going in was pure oxygen, which can happen if you have a closed system. But in this case, you still are having the nitrogen gas be warmed up to a higher temperature, the same temperature that everything else is coming out as. And so with this knowledge, well, don't you think taking out that nitrogen would remove some of that energy needed to heat up the nitrogen. So if we want our enthalpies to be the same and accurately calculate for the final temperature of what's coming out and our system going in is nitrogen, it contains nitrogen, we can't just eliminate it. All right, and so, well, I need to put in my 79/21 nitrogen and 2. And so we're going to balance this, blah, blah, blah. We've got, I'm going to put 2. We're going to put 2, 2, and then 2 here. I think. That seems right. And so the thing about this is that this is just for, oh, I put methane. Whoopsies. Okay. Is that this is just for with methane. And so we're going to do the same thing with ethane. And so we're going to have 79/21 and 2 plus C2H6 plus O2 get to CO2 plus H2O plus, oh, my arm. Oh, gosh. My arm's starting to hurt a lot. And so we're going to balance this out. And so in this case, we're going to have 7/2. We're going to have 7/2. Then we are going to have, I think 7/2 over the other one. And yeah, so 3, 7/2. Okay. And finally, for propane, bear with me. I know this is a lot of writing. Plus well, that's propane, so C3H8 plus O2, CO2 plus 3H2O, not 3, plus 79/21, and 2. All right. Ooh, okay. So, pardon me. So now we're going to balance that one, which is going to be, if I remember correctly, 5, 3, 4, 5. I believe that is correct. And so what we're going to do from this is that we are going to talk about the equation that we need for calculating the enthalpy at the end. And so yes, we know that it's equivalent, but in order to be able to find that temperature, we need to figure out that enthalpy. And so we have our enthalpy. Oh, that's big. I don't need it that big. We have our enthalpy. And let's say our final temperature is going to be 2000. Okay? So our temperature at 2000 Kelvin is equal to, and it's going to be equal to, well, this is our enthalpy of, let's do CO2. Because you can only find, it'll only be helpful if we find each component and then we can pull it all together, because you can't really find the enthalpy of an entire system straight up. Like when it comes to like CH4, you can't put it into a system and then expect it, you can't put carbons and hydrogens and expect it to create CH4. That doesn't really work. And so what we can do is we can do CO2 and we can do H2O, and you can balance it so that you can find out the enthalpy at a certain temperature of your carbons and the hydrogens, and then push it together to get your CH4 or C3H8, whatever. And so that's what we're doing here, but this one's, we're just going to talk about CO2. And so this is going to be equal to our H of CO2 at, let's say, 300 kelvins. Well, let's do room temperature. That'll make life easier. So 298. And that is, it's going to be that plus the integral from 298 to our 2000, 1, 2, 3, and that is going to be the integral of that, our CP dt. All right. And so, well, you can look up, if you look up the equation, I already know the equation, and I don't want to waste your time by me searching up in the search engine the equation, so I'm just going to write it, but that CP can be calculated as A plus B C over T over, I think it is, yeah, it's, I was making sure if it was sine or cosine first. Sine, hyperbolic sine of C over T, all of that is squared plus D E over T over cosh of E T squared. All right. And so that is our CP based on, when you look it up, equation 107. I'm just saving you the time of looking it up. I'm just letting you know that that's what I'm doing, because life, you can use any, you are able to use notes in real life. So, and from this, we are going to integrate it. And so with integrating, well, we don't want to integrate that. And so again, our professor is kind enough to let us look this up. Wolfram alpha, I'm not pulling it up just because editing issues later. So the integrating this is going to end up being A of T plus B, B cotangent, hyperbolic cotangent. Oh, wait, no. Okay. B times C times cotangent hyperbolic of C over T. And then the second part is the pretty much the same thing, but with the other units. And so it's going to be D times E of, this is just going to be hyperbolic tangent of E over T. And so that is our integral. And so what we're going to do is we are going to put that into our Python code, and we will end up using this to find out, it'll end up being where this is just an empty blank, and that is a variable we're looking to find. And we know where this is, and so we will use root solver. And we'll talk about that more when we get into the code. All right. Now it is time for us to code everything we just solved in Google Colaboratory, aka Python. And so what I have done here is I have cloned in chem tools, and so that we can get all of our values that the system has for our methane, ethane, propane, all that jazz. And so that's what this is doing right here. And then down here, we're making life easier for numpy as np, so we don't have to write out numpy. Same thing with tools.che, it just says che. And then scipy optimize, importing the root for the root solver at the end. And so first things first, we've got to insert in our properties, and we have parentheses and then brackets. And then we are going to put in every single one of our components that we have in the system. So we have methane, ethane, and propane. That's just the way the system recognizes it. Oxygen, And then we have nitrogen. And then we have carbon dioxide, all one word, not with a space. And then we have water. All right, so methane, ethane, propane, oxygen, nitrogen, carbon dioxide, water. I think that's it. Boom, boom, pow. Yep, okay. And so what we're going to do first is, well, after that, we are going to insert in our integrated equation that we determined, and this is going to be in the definition of a equation that we're going to name delta H sense ideal gas, and our independent variable is T. And so I made my life easier, and not to mess up, I copied and pasted that. And so this is basically just our integrated equation that we talked about with our A values, and like A, B, C, D, and E. And so, but our P dot CP IGA or IGB, that is basically taking what we did as P, because we inserted in all of these to be P. So we just have to do P dot what we want, which is the CP IGA, and then the value, which is, well, the A or B. So that's just what that is. And this is making my life easier. And then you divide it all by 1,000 because of unit differences. And that should be good. I was concerned that I was going to mistype and then make everything a lot more difficult for me. So now what we're going to do is we are going to put in our information for our formula. So this is our balanced chemical equation that we worked on for each one, and then also using our fuel formula to get how many moles of each item there are. So we are going to go fuel formula, straightforward, if I can spell, is equal to NP dot array. And these are our values that we are given by, well, I was given by my professor. And so this is basically, oh wait, no, never mind. That's N fuel. Don't listen to me. So this is just putting in our coefficients for what we did with the balanced equation. So that's going to be parentheses, what was it? Because it's 1, 4, end bracket, comma, enter. And this is just making it a column. 2, 6, end bracket, enter. Well, I forgot the comma. There we go. And then this one is 3, 8, end bracket, and parentheses. And then now we are putting in our N fuel, which is what I jumped the gun on when explaining the fuel formula. Our N fuel is the number of moles of each component of the fuel. So we are given this by my professor. And so we have N fuel is equal to NP dot array, and it is 10 moles of methane, 10 moles, I got that dot at the end. Methane, 1.5 moles of ethane, and then 1 mole of propane. And then with this, we are going to solve what each of the moles of our units are. So our moles of carbons and our moles of hydrogens is going to be equal to our N fuel multiplied, which these are we're multiplying matrices, and so that's going to be the at symbol. And so we're multiplying that by our fuel formula. Oop. Okay. And so now we can do what our N carbon dioxide or moles of carbon dioxide, and because in that equation the only thing that contains carbons is the carbon dioxide based on the beginning, that means that our moles of carbon dioxide is just going to be moles of carbons. No, don't automatically do that. Okay, and so now we can do our moles of H2O, And so that is going to be equal to our moles of hydrogens divided by 2, because we have all of our hydrogens in an H2O. There's already a 2 there. We know that. Multiply by 2 based on the balancing of the equation. So that's moles of hydrogens divided by 2 to get moles of H2O. And then our moles of O2 is going to be equal to our moles of carbons plus our moles of H2O divided by 2. And then we have our moles of nitrogen is equal to that ratio of 79/21 relating to oxygen with respect the ratio of nitrogen and oxygen in the air. And that's multiplied by our moles of O2. I need to capitalize that. I think that's good. No. Oh, I'd do that. There we go. Okay. And so from this, we are going to put in our moles of feed that is happening. So this is our moles of feed going in. And so if you think about this, we are concatenate is the term that the system uses, but we are combining all of our moles of certain compounds into one for the beginning and the end products. And so our beginning and end, all you will have sitting in there in the array, because it'll be an array. It'll have our fuel, our end fuel, which is our array of the 10, 1.5, and 1. And then we have our moles of oxygen, moles of nitrogen, moles of hydrogens, moles of carbon dioxide, H2O, all that. And so what we're going to do is we are going to do this one, which is going to be NP dot concatenate. And so this is just combining it all with N fuel, comma, NP dot array, parentheses. And so we have our moles of oxygen gas, our moles of nitrogen, and then in our beginning, we don't have any moles of carbon dioxide or moles of water. So that's just going to be 0 and 0. And make sure you have all of those parentheses and brackets. And so now we are going to make our moles of product, which is going to start with the exact same thing, NP dot concatenate, parentheses, and then it's going to be, we're going to create a line of zeros, because this is just making up for the fact that we no longer have that fuel, and so that's just going to be a line of zeros. And so we are going to go well, NP, if I can type, dot zeros underscore like, and that is going to be N fuel. So that's just creating zeros that of the length of our N fuel array. And so we do that with NP dot array at 0, our moles of H2, our moles of carbon dioxide, and our moles of H2O. And that should be good. Let me shift enter now. Oh, I'm dumb. That's the slot for N2. Okay. So from this, we are going to start making that final equation. So this is just basically setting up our system and our values of moles going in, coming out. And so what we're going to do is we are going to go back up here and right here, let's add a code, and we are going to create another function. So we're going to call this enthalpy of ideal gas, and our independent variables, the moles and the temperature. And what this is going to do is this is just going to give our enthalpy depending on the amount of moles that we give in and the temperature we give in. And so we are going to put in return. This is a pretty long one, np dot. So this is creating a dot product, n comma p h heat of formation of ideal gas. Ugh. I got stuff in my eyes. Ideal gas plus our NP dot of our moles, comma, delta H cents IG, and that, well, of T, when you put in that unit, minus our delta H of cents of our IG starting at 298. So this is basically giving us the amount of heat in the what's my issue? Keyword can't be an expression. Oh, because I meant subtract. Shift enter. Is that good now? Okay. And so what we can do with that is we can come down here and put in our enthalpy ideal gas of N feed. So this is what's going in, and that in certain temperature, let's say 300, because our problem, we are given that the temperature going in the system is at 300. So let's do that. What's the issue? Name HFIG. Oh. P dot. Shift enter. See all these little mistakes. There we go. And so our enthalpy for the feed coming in, that's going to be negative 969,527 joules per mole. And so what we're going to want to do from this is that, well, we talked about how it's adiabatic, there's no loss of heat, and that means that the starting enthalpy is going to be the same as the ending enthalpy. And so, yeah, we could use that equation and insert in different temperatures and try to get it to match, but we're going to make life easier because we have a system that can do the math for us instead of us just guessing. And so what we're going to do now is we're going to create another function, all the functions today, and we're going to do energy. And so what we are going, I need a colon. What we are going to return is going to be the heat of ideal gas of the N feed at 300 minus the the enthalpy at end product at a specific temperature that we want to find. Shift enter. And so with this is where that last root solver comes in, finishes up the whole thing. We are going to use root of our energy underscore equation, that with, so we can put in our 300, shift enter. So this right here, that is our temperature All right, so if we come up here, well, down here, and put an HIG of our end product, comma, with 2, 3, 4, 8, shift enter, and that's of course without all the decimals. That's pretty close. And so basically this right here, let me just type the rest of it in to prove my point. 5, 4, 8, 4, 2, 0, 0, 8. There we are. So look at that. 0.11225. And so it starts getting a little bit weird after that point, but that's going to happen with any rounded answer. And so if you see, what we just did is we put in all of our information that we just talked about and created formulas to solve for the enthalpy, and then used our knowledge of adiabatic equations to find what the final temperature, the maximum temperature of the system can go. And so it could be increased by having pure oxygen going in instead of having that nitrogen, because as we talked about before, that nitrogen is going to have to be heated up. And so if the nitrogen wasn't there, our heat of the system, or the temperature of the system, could increase more. But because of the enthalpy having to be the same and having that nitrogen there, it's limiting the amount of the temperature that the system can go. So that has been adiabatic flame temperature. Thank you so much for watching. And this is the last video I have with this course. And so just thank you for sticking along with me.